Hello, my name is Caitlin Stewart, and this is my Module 6 Mastery assignment for AP Calculus. So to start off with, we were asked to find two subjects from this module that we thought were going to be on the AP test, and the first one that I chose is slope fields. To start us off on slope fields, I have some helpful notes. So a slope field is a sketch of the solution to a differential equation. Most of these use the first derivative to create the slope field, and on the slope field, the line segments show the derivative as the slope of the tangent line. And the slope of the line segments is the sum of the x and y coordinates based off of the first derivative equation that is given. These line segments are short and they don't intersect on the graph. And when the slope is equal to 0, you have a horizontal line segment. Whenever there's negative slope, your line segment falls from left to right, and whenever you have a positive slope, it rises from left to right. And there is the same relative steepness for positive and negative slopes. So when you are reading a slope field, there's some helpful hints to make sure that you understand what you're seeing. So first of all, you want to look and see where you have your horizontal slopes, or where your slopes equal 0. You want to see where your line segments are positive versus negative. You want to see what your slope field is doing along the x-axis, or whenever y is equal to 0. And then you also want to do it on your y-axis where your x is equal to 0. And you want to try to figure out if your slopes depend only on x, if they depend only on y's, or if it's some combination of the two. So an example I have here is negative x over y. And as you can see, this is the slope field picture that I chose. And very simply, what you do is that you choose a point. For instance, if you do 1, 1 right here, if you have the coordinate 1, 1, then you would have 1 as your x, 1 as your y, and it would be negative 1 over 1, which is simply a negative 1. So therefore, the slope falls because it's negative, and it's a negative 1, which is about the same relative steepness as some of the other ones. And you would simply do this for every single coordinate along the plane until you reach a graph of whatever size you need to find. And this is just one example. The second topic that I chose were separable differential equations. And so to start us off, I have some vocabulary. The initial condition is any point on the solution curve that indicates which particular member of a family of functions is the solution to a given differential equation. The solution is a function that has its derivative a given differential equation represents the fact that an entire family of functions all have the same derivative. The general solution, which is the family of function that all differentiate to a given differential equation. And the particular solution, which is a solution to a differential equation given an initial condition. And this diffeq is just a shortcut or a shorthanded version of a differential equation for future reference. Some helpful notes. In order to find these separable differential equations, we have some simple steps. Separate, integrate, then solve. And so to start off with, your separate, all you're going to do there is you're going to put all of your one variable to the left side of the equation and all other variables on the right side. Then your next step is to integrate, which is just very simply to integrate both sides of the differential equation with the separated variables. And then your third step is just going to be to solve. And at this step, you're just going to solve for y, which is going to be rearranging and algebraically solving for y. As a side note, not all differential equations can be solved this way, because not all differential equations can be separated. And so for these differential equations that cannot be solved in this pattern, you just study using slope fields. So some applications of separable differential equations is they're very vast, but to start off with, we have position, velocity, and acceleration, and you use gravity, but this is just it's just another step further into the same things that we've been doing. You can do it with growth and decay differential equations, where a current quantity is changing at a rate proportional to the amount present. For instance, bank rates. Another one is Newton's law of heating and cooling. So for instance, finding how fast food from the oven will cool in a given temperature. So just some different applications of these. And so finally, we have an example. And this is dy over dx of x squared over y is equal to x squared over y. And if you'd like to pause it here and work it out, you can. And so now I'm going to show you the answers and show you how you get through it. So here's the solution. If you start off with this first equation, then the first step is to separate, which is to get all of one variable on one side. And so in this situation, you're going to multiply by y over here, so that all of your y is over here and you just have x over here. And then you're going to multiply by your dx so that you have all of your x's over here and all of your y's over here, as you see right here. Then you're going to integrate these two, so you end up with this, which is just the same things that we've been doing. And then you're just going to algebraically solve for y. So you end up with y is equal to plus or minus the square root of 2/3 x cubed plus c. And this plus or minus and the c will be determined by what point you're trying to find a particular solution at, or whatever the application is will determine whether it's positive and negative and what your c is and that kind of thing. So, thank you for listening. I hope you have a good day.